So we've covered the preliminaries on spring mass systems, and we're going to consider the first class or sub case of spring mass systems of the free undamped motion. Okay, so this is kind of the simplest scenario. What does that mean? Well, free motion of a spring mass system is motion in the absence of external forces. Okay, the driving function is zero. So we have to consider what's internal to our system. Any dissipative force, resistive force, like frictional force, from, say, the spring mass flowing in a viscous fluid, or having friction between it and a surface that it's moving on, we'll consider that as part of our system in general. Okay, the spring, of course, is part of our system. And so what we specifically mean here is there isn't some external unit attached to the spring mass system just applying a certain force. In the case of differential equation, it just means that it's a homogeneous equation. Okay. Undamped means the absence of resistive or frictional forces. Okay. So Newton's second law, F equals ma. A is the second derivative with respect to time of position. So that's your ma there. Now, the only forces, the sum of the forces, just that being applied by the spring there. And by Hooke's law, that's equal to negative kx. So you can move this k to the other side and you get this differential equation, second order differential equation. And, these are parameters. M and k are parameters in our differential equation. That means they're constants, okay? They're constants that, depending on the system, you just choose at the beginning and you fix, okay, while you're doing the analysis. At least if you're dealing with a system, that has a constant, spring constant, for example, not one where the stiffness is changing, which we could modify and introduce. But here we're just considering them constants. Divide by m to put in standard form. And now looking ahead, we're going to define omega squared as k over m, okay? Or that omega is equal to square root of k over m. This will be the angular frequency. We see that, and we just define it from the beginning as there, okay? So how do we solve this? Well, we get an auxiliary equation. Again, omega, even though it's a letter, is considered a constant. So you just treat it as if it was some number. And you get complex conjugate roots. And so the general solution to this homogeneous equation will look like this, where beta is omega and alpha is 0, in this case, for the complex number. And if we apply our initial conditions, we'll get the equation of motion. That's what the equation of motion is, okay? It's just applying the initial conditions on the general solution and solving. That's what's called the equation of motion. We may also use the other notation that we looked at if instead of wanting to look at that sum, we could combine them into instead of the parameter of C1 and C2, we have now the amplitude and the phase, as we've discussed before, where you get them from these formulas. We may, and these are not very instructive in a physical sense, C1 and C2, okay? But instead, something like the initial position and the initial velocity, these are physically instructive. Okay, so we may prefer to use them instead of C1 and C2, and if we do, so if we start with at t equals 0 position x naught, and at t equals 0 x prime, the derivative with respect to time, that's the velocity, so the initial velocity v naught, what we could do is take this form and apply the conditions on it. This will give us that x naught is equal to a cosine phi. V naught is equal to this. Okay? And now what you could do is, divide this by negative omega. So you'll get V naught over a negative omega. And you'll have an a sine phi and an a cosine phi. Square each of those and add. The cosine squared plus sine squared become 1. And you're left with a formula for a. Okay, that's how you would get that. And tan phi, on the other hand, well, that's sine phi over cosine phi. And so you take these conditions and you solve and you would get this. Okay, so that's how you could get the phase angle. And, this is just more instructive for physical purposes than C1 and C2, which don't carry much meaning, but these do. So the motion that we get from this equation here, okay, just in general, is simple harmonic motion. That's just called simple harmonic motion, okay? And it looks sinusoidal, which means, it could be cosine or sine. It looks something like this, okay? That's how simple harmonic motion looks. Or if you will, like, you could have the unit circle or with an arbitrary radius with a vector rotating around, and you look at projections on the axis. Same kind of concept there, especially if you think about Euler's formula. But anyway, so that's simple harmonic motion, and some key terms there with simple harmonic motion shown graphically. The amplitude is the farthest distance away from the equilibrium. Okay, it's also called the extreme displacement. Okay. No, it's not from the top to the bottom. It's from the top to the equilibrium, or 0. Okay, so that's what the amplitude is. So this is the amplitude. That's the amplitude. Okay. We also have the angular frequency. Okay, and that's related to the period. The period is the time it takes to complete one cycle. So to go from the top here to the top here. Okay, sometimes people get confused and think about 0 to 0, but that's not the case. You would have to go back to 0 here. So here you're going down, but here you're going up. So that's actually half of a period there. Okay, but from peak to peak, that also works and gives you the period. And this is its relation to the angular frequency. Frequency, the natural frequency, or or just the good old-fashioned frequency, you could say, is 1 over the period, and omega is equal to omega over 2 pi. So that's how to relate frequency with angular frequency. And something that's not shown in this plot is the phase, okay, this term here. And the phase is just, so if it's positive, it's this shifted to the left, okay? And if it's negative, it's this whole curve shifted to the right. It's how much you're shifting to the left or right, okay? That's called that's the information that you get from the phase. Okay. So let's look at an example. So here we have a mass weighing 2 pounds, stretches a spring 6 inches, and at t equals 0, so we're getting the initial conditions here, is released from a point 8 inches below the equilibrium position, okay, with an upward velocity of 4/3 feet per second. Determine the equation of motion. And note that, and this is a rather important point, so please do note it, we're going to consider plus x to be pointing down for our purposes, okay? We're going to consider the positive x to be pointing down. Well, this problem is giving us a hanging mass, and one may wonder, hey, we've looked at Hooke's law before with a mass that just translates left to right. What's the effect of gravity? We'll get an extra term in our differential equation. Well, it actually turns out to just shift the equilibrium position, but beyond the lower equilibrium position, you may ignore the effects of gravity. Okay, and you could see that here. So if this spring has natural length L, we put a mass on there, and it stretches S. So here now we have a mass on here, okay? And we consider X to be what it stretches beyond L plus this extended length due to the force of gravity, okay? So here it's in equilibrium. So this S is defined where this is in equilibrium. So the force of gravity is equal to the force of the spring there. Equal and opposite. And X is what's stretching beyond that. Okay? So if you look at the differential equation with that, you get, negative K X plus S is how much it's stretching beyond the natural length, right? But you now have a plus mg. And again, we're considering the up to be negative and down to be positive, and so that's why you're getting this plus mg. Distributing that k, you get negative kx, x again, the length beyond L plus S. And now this is 0. Why is it 0? Well, because at equilibrium, which is what defines S, you have that ks in magnitude is equal to mg at equilibrium. That's how we define S, okay? It's what's stretched for, it's how much the spring is stretched at equilibrium. And so these cancel and you get this differential equation, okay? So what can we say from all of this? What we could say is what gravity does for a spring mass system that's hanging is just merely shift the equilibrium point. Beyond that, the dynamics are the same. We could just ignore it, okay? So we just redefine our x to be what's extended beyond L plus S instead of just L. And beyond that, we could just forget that it's there. Okay. So let's extract the parameters from the word problem. The weight is 2 pounds of this mass. It stretches half of a foot, okay, or 6 inches, half of a foot at equilibrium. Okay, that's implicitly understood there. The initial speed is upward at 4/3 feet per second. Okay, there, upward. And why is that negative then? Well, it's because we're taking the plus x to be down. And it starts 2/3 feet below the equilibrium. That's why that's positive there. If it was above the equilibrium, it would be negative. In G, we're using feet per second square. And, that's kind of unconventional. You generally will use SI units, but you get problems like this. And so let's use it. So first we need the mass. Okay, that's just one parameter that's important for our omega. So to get the mass, you just take the weight and you divide by gravity, okay? Because weight is equal to mg. That's an approximation to Newton's law of gravitation. And you just apply. So weight is 2 pounds divided by 32 feet per second. Now, when you do that, these units give you a slug, okay? Slug is a unit for mass. Generally, kilogram is the more conventional, but if we do use these units, we actually end up with a slug. So now you know it. K, the stiffness. Well, for the stiffness, we look at the force that you apply and the extension of the spring. The force that the spring applies at a particular extension or contraction. Okay, and we're told that this spring will be in equilibrium with gravity if you take if it's extended 6 inches, it'll have to apply 2 pounds. That's the only way to get to equilibrium. And so we have this 2 pounds here, and we have 1/2 of a feet here, 6 inches, and you get 4 pounds per feet for the K. So now we got our K, we got our M, we got our important parameters, and so we get omega squared, and we have the solution from up here, okay? Or we could just redo it. We don't have to look at the equations. We get this differential equation. All right, that's a homogeneous differential equation with constant coefficients. And you will get this general solution, okay, with 8 there. Okay, you could get that from the auxiliary equation if you don't want to just use the formula. You'll have the square root of 64 plus or minus, and you'll get complex so it's square root of negative 64, and so you get complex conjugates. And now we apply our initial conditions. When we do that, we get C1 needs to be 2/3, and we take the derivative of this x. Okay, now when we take the derivative, we have a velocity. Okay, so if it's not shown here because I just plug in 0 right away, but we could just take the derivative of this, and you'll get C1 omega negative sine omega t and C2 omega cosine omega t for the velocity. And so you apply, and then you plug in t equals 0 into the derivative. That's important. You don't plug in 0 and then take the derivative. You take the derivative and then plug in 0. And you apply the initial condition for the velocity, and you get that for C2. And so we fix C1 and C2 by the IVP for the initial value problem, and we get that for our solution to the initial value problem. I remark here that you could instead use that notation, but we have the formula for that. Since we're using the sine, we got to be careful that tan phi is equal to C1 over C2. Okay, and so you would get that phase. By the way, if you take arctan, so this is equal to -4. If you take arctan, put it in the calculator, it gives you this. But we need to be in, so that's giving you the term that would be in the 4th quadrant. You got to be careful with arctan. It gives you terms, if you put it in a calculator, that are in the 1st or 2nd quadrant, and so it ignores the 3rd and 1st or 4th, and it ignores the 2nd and 3rd. You actually have that sine phi is equal to C1 over A. Okay, so it's proportional to C1 when you're using this sine, okay? And cosine is proportional to C2 over A, okay? So we have then that C1 is positive. Okay, so sine phi is positive, and cosine phi, C2, is negative. That's the 2nd quadrant, okay? That's the case of the 2nd quadrant. So we shift this angle, which is in the 4th quadrant, to the 2nd quadrant, and we do that by adding pi to it, okay? That just shifts it all the way opposite if you're looking at this in a unit circle, and you get 1.816, okay? So be careful that with sine, you actually have C1 over C2, not C2 over C1, okay? And so we're flipping around these adjacents and opposites, and that could get confusing. Nevertheless, this would make that clear, these two relations, okay? Then you'll have clearly what is sine and what is cosine. Even though they're the opposite if you were writing x in terms of cosine instead of sine there. So something to pay attention to there. Easily slip up.